Solids, liquids, and gases have different properties. The high energy particles of a gas have enough energy to overcome the forces of attraction that would keep them together otherwise. The lower energy particles within a liquid don't have that ability. They can't generate the force to move away from each other quite as easily. You've also seen the sweat that forms on the outside of a cold bottle of water. Every time a water molecule in a gas state collides with that container, that surface of water, it's going to transfer energy. And the gas molecule moves a little bit slower. The water molecule can absorb that energy and move a little bit faster. Therefore, gas molecules can get trapped by a liquid, and molecules in a liquid can get energized in order to escape. In this part of the lesson, you will learn about the way that molecules behave inside a liquid. According to kinetic molecular theory, the particles in a liquid have enough energy to stretch the forces that are holding them together, the attractive forces keeping them in liquid form, but they don't have enough energy to break those interactions. And therefore, the kinetic energy is comparable with the strength of the intermolecular attractions. This brings the particles closer together, and as a result, liquids are denser than gases. This also has an impact on how they fill their container. They have a fixed volume, and they're not compressible. If you add pressure to a liquid, the volume changes only slightly. So it's not like a gas that will expand to fill its container. Also, the particles are not fixed in place as they would be in a solid. They're able to flow and slide by each other. Therefore, the particles in a liquid can take the shape of the container that holds them. The force of gravity pulls them down, and they fill the bottom of the container. Recall that the particles in matter experience intermolecular forces, attractive or repulsive forces due to molecular dipoles or uneven electronic distribution. Take a look at the picture on your screen. Let's say that the blue parts of the molecules represent a negative dipole or a negative partial charge, and the pink parts represent a partial positive charge. Well, because they have different dipoles, this can affect their interactions, how the molecules move and associate with each other. You can have attractions between the molecules, and you can have repulsions between those molecules. The stronger the intermolecular forces are, the more kinetic energy molecules must have to be able to overcome those attractions. The particles in a gas have enough kinetic energy to overcome the intermolecular forces between them. If the gas loses energy, for example, when a gas is cooled, eventually their kinetic energy becomes insufficient to overcome the intermolecular forces. The particles now attract each other more easily, and the gas condenses into a liquid, changing the state of matter. The opposite process can also occur. If the particles in a liquid gain enough energy, for example, from being heated, then their kinetic energy overcomes the intermolecular forces between those molecules. The liquid boils or evaporates to become a gas, and the state of matter changes. Evaporation happens at the surface of a liquid when a small number of molecules gain energy due to random collisions. Boiling happens throughout the volume of a liquid when large numbers of molecules attain enough energy to overcome the molecular interactions all at once. Because the strengths of intermolecular forces determine how much kinetic energy is necessary to overcome them, we could expect that the boiling point would correlate with the intermolecular forces, and this is what we observe. Substances with strong intermolecular forces such as ionic compounds and polar covalent compounds, tend to have much higher boiling points than do nonpolar covalent compounds. Ionic compounds have higher boiling points than polar covalent compounds because ionic bonds are much stronger than dipole-dipole interactions. Intermolecular forces affect particles at all energy levels. And as we just saw in the last segment, that particles can go from a liquid to a gas form or a gas to a liquid form depending upon their energy relative to the intermolecular forces pulling them together. Now, in a liquid, the particles are in constant random motion. They're sliding around each other, and they're getting pulled by those dipole moments, by those electrical interactions, and getting pulled together with the intermolecular forces. But they have enough energy to stretch those forces, and therefore they can slide past each other. They're always in motion. This is compared to a solid, where the particles become fixed in place. Instead of sliding past each other, they only have enough energy to vibrate in the same place. Now, when you freeze, you lose energy. The particles give up their energy, and therefore they go slower. When they're going slower, they can get trapped by the intermolecular forces and fixed in place. The reverse of this process is melting, and therefore if you increase the kinetic energy of those molecules, they can vibrate more, and when you have enough energy, you break free from the intermolecular forces, keeping you in one spot, and you can move to the liquid phase, where you have enough energy to slide past the other molecules and not get stuck in one place. You've just learned about the particle interactions that exist within liquids. Now, even objects that we normally think of as solid will liquefy if you heat them up to the appropriate temperature. The balance between having just enough energy to move around and not enough energy to break free gives liquids a very unique set of properties. As we can see, what we have here in the picture is liquid gold. If you heat it up hot enough, even metals will liquefy. What are these properties of liquids? That is the focus of this next segment, the macroscopic properties of liquids. When a liquid flows slowly, we say that it's viscous or has a high viscosity. What do we mean when we say this? Well, this describes the thickness or the resistance of a liquid to flow. Now, kinetic molecular theory explains this by the balance between those intermolecular forces and the energy that each particle carries with it in order to move freely. Does it have enough energy to escape as a gas? Does it have enough energy to only slide past each other? Or does it not have enough energy to do much more than vibrate? Well, there's a couple different factors which affect a liquid's viscosity. First, it's inversely correlated with temperature. As temperature goes up, the average kinetic energy of those molecules, of those particles within the liquid, increase. As they increase, they have more energy to overcome the intermolecular forces. So therefore, it becomes more fluid, more liquid, less viscous as the temperature increases. Now, if temperature decreases, it becomes more viscous, more thick, more resistant to flow. Second factor is that viscosity is directly correlated to the size, or more precisely, the mass of the particles. As the mass increases, we see the viscosity increase. When the particles are smaller, the viscosity is smaller. And this makes sense as well, because in a certain volume, there's more freedom to move when the particles are smaller versus larger. Lastly, Viscosity is directly correlated with the strength of the intermolecular forces for that substance. Why does that matter? Well, different substances are going to be made of different chemicals, different molecules, which are going to have different amounts of electrical interactions, different intermolecular forces within them. So as the strength of the intermolecular forces increases, so does the viscosity. Surface tension is another property of liquids, and this is the tendency of a liquid surface to resist penetration. Now, you're too heavy to walk on water, but many insects don't have as much mass and can effectively walk on the surface of a sample of water. Why? Because you have these interactions between molecules, pulling them together in the interior of a liquid. But along the surface, you get interactions which form this delicate skin. There's nothing to interact with over here, so they pull on each other at the surface even stronger than on the interior. This is how water droplets get their spherical shape. They want to minimize interactions, minimize the intermolecular forces with outside the barrier, and increase the number of interactions on the interior. Therefore, you get the spherical shape. Now, surface tension is directly correlated with intermolecular attraction. When the strength of those forces increases, so does the surface tension of the liquid. You can break these up with a surfactant. These are substances that can interrupt those intermolecular forces and therefore break the surface tension. A common one that you might use is dish soap. Now, looking at other properties such as compressibility. We looked at gases, and gases are highly compressible. Liquids are not. For all intents and purposes, we can say that they are incompressible. And how does this help us? What applications does it have? Well, it allows liquid to transmit forces through them, like in the hydraulics of car brakes or the flaps on an airplane, construction equipment, robots, where you're moving very heavy lever arms and you need to transmit force. Liquids are ideal because they are incompressible. Now, another property of liquids is their ability to dissolve other substances. They can dissolve solids, they can dissolve other liquids, they can also dissolve gases. How does this work? Well, in a solution you have a solvent and a solute. The solvent is the host liquid. And when a solid, liquid, or gas becomes integrated into that host liquid, it's said to be dissolved. Okay? The particles will eventually become dispersed among the liquid particles as they break up and move from high concentration to low concentration and eventually become part of that liquid. So liquids can dissolve not only particles, but also other liquids and gases. When one liquid dissolves another, it's called a miscible liquid, which means they can dissolve in each other, as opposed to immiscible liquids, which cannot dissolve each other. When you try to mix them up, the particles remain separate. This is a familiar example of oil and water. Why does this happen? Because the intermolecular forces of one substance don't like the intermolecular interactions of the other substance. What do we mean when we say doesn't like it? It means that they repel each other. When those molecules repel each other, you get separation or immiscible liquids.